Right, in term 1 we looked at scalars and vectors as quantities. A scalar was a quantity that had just a magnitude or a size, whereas a vector quantity was one with a size and also a direction. So the key thing was you would also have a direction involved with it. So there are a few examples that we discussed very briefly in term 1. You could have just the length of the table being 1.2 metres, it didn't really matter which direction that was in, whereas a force might be acting downwards, so that was a vector quantity. Speed on a car is only getting 60 kilometres per hour with no sort of direction, whereas a velocity would quote a direction as well, in this case south. And there's some others there that we actually sort of covered very briefly. You've got temperature, time and mass as being scalar quantities, resistance in a circuit, and the distance travelled. Whereas you could also be doing acceleration has a direction there, displacement has a direction, and there's several others we can look at, the gravitational forces and gravitational fields. So we now want to focus on the vector part of it here, so let's look at some. So if you represent a vector with a arrow at the end of a line, so this particular one I've got here, vector A, we represent that as being 6, it might be a velocity of 6 metres per second or a force or something like that. So you draw it to a certain length, maybe 6 centimetres here, and the arrow says it's going off to the right. So I've got a size and a direction based on the length of the arrow and also the fact that I've got an arrow pointing which way it's going. So in the past when you've been adding things together, so let's say you had a velocity of 6 and we said we've increased the speed by accelerated the car by 3, so let's say we actually increased it by 3. We've always been doing it in a straight line, so the total vector was actually 9 metres per second. So if you started off with a car of 6 metres a second, you increased it by 3 metres a second, we've gone for 9. And we're really just doing speeds there rather than true vectors, because we're allowed to do them in the same line, so they're the same answer. When you add vectors in reality then, you need to consider which way they're going. Now in this particular case, we've got them travelling in the same direction, so you would get the same answer, because when you add vectors, you always add them tip to tail. So to go to the tip of the first vector, you would add the tail of the next one here, and add that on there at the end, and in this case, we're going to get the same answer, all right? If I asked you to do, say, A plus C then, you would do A is 6 off to the right, and you would bring the C back 2 in the opposite direction, because this C here is 2 to the left, so at the tip of the first vector, we go backwards in the direction of the C, which is 2. So the final vector would be from the start of the first vector to the end of the last. So that's actually the answer for A plus C. The answer would be 4, and you would just do 6, 8, 2 on a calculator if you could work that out, and it's going to be off to the right. So that's the result of A plus C in the same direction. So that's relatively easy. If they decided to give you a vector and said, okay, we want to do 2A, you're going to do A, which is 6, plus another 6 on the end there. The answer to A plus A is actually 12. So the easiest way of actually multiplying a vector, if you want to multiply a vector, is you just actually increase the size by the factor it tells you. Here if we're doing 2A, we're going to double the actual magnitude. So we're going to double the length of the vector we draw, the size of the vector. If they said it was 3A, you would triple it. So in this case it would be 3 sixes would be 18 to the right. If they said to halve the vector, and say with half A there, you're going to do a half of 6 would be 3, but still in the same direction. If you're asked to do, say, minus A, now A is normally off 6 to the right, minus A would be 6 to the left, you'd reverse the direction. So when you're doing negatives, you need to reverse the direction. So reverse the direction for a negative. So they're the basics. If you are given questions here where the direction clearly is starting to be taken into account, what would you get if you were to do something like a B plus D? If you're actually given B plus D, let's have a look at that. We're going to be doing B is 3 off to the right here. This B is 3. At the tip of that vector, we're going to add the D, which is 4 going down there. And the total then would be the start of the first part of the vector all the way down to the end of the last one. I'll draw a double arrow and the angle there. This would be a 90 degrees if I've drawn this right. So this is going to be B plus D here. That value there. That's going to be a total. So to get that there, we would use Pythagoras' theorem. The answer is going to be 3 squared plus 4 squared, all square rooted. Now that's actually going to be 5. It's a 3, 4, 5 triangle. If you want to get the angle though, you need to be basing this on the fact that tangent of theta is the opposite side over the adjacent side. In this case, the opposite side would be 4, and the adjacent side, the one alongside here, would be 3, not the hypotenuse side, that's the long one. So the adjacent side here would be one alongside, which is 3. So you're getting tan theta equals 1.33 recurring. Okay? To get theta then, you would need to do tan to the minus 1 or inverse tan or shift tan of that number. Alright? And if you do that there, you will get 53.1 degrees. Now, how would this differ if we had changed this question to be take D? What would you do then? So if you look at it, the B would still be 3 to the right, as before. But to subtract D, we really want to add D in the opposite direction. So it's going down here, we need to go up. You subtract D is 4 upwards this time. And again, you're going to do the same sort of thing for the total. We're going to go like that. Now obviously that's going to be the same size. It's still going to be 5, and it's still going to be an angle here of 53.1 degrees. 53.1 degrees. You're still getting a size of, as an answer, equal to 5. B take D equals 5. But it's now going up in the opposite direction, so there's any difference there. Alright. So if you were asked to do something like 2B take away 3D, how are you going to do a question like that? So you need to look at the 2B as being double B there, which is going to be 6 off to the right. So there's your 2B. And the take 3D, I have to move this. You take 3D, is going to be D in the opposite direction because it's subtraction, but you've got to do 3 times 4, which is going to be 12 going up. So we want to go 12 up there. Okay? So there's your vector we're trying to work out. So as a total here, we're going to go start of the first vector to the end of the last part. Yes, you get your answer there. Let's say these are velocities we're trying to work out here as a total. The total velocity there then would be the Pythagoras' theorem again. The square root of 6 squared plus 12 squared, and you go from there. And if you're doing the angle, again you'll use that tangent idea. You have to do shift tangent, but it's opposite side over adjacent side. And you get an answer to that. So just be aware of those sort of things. So if we look at some real examples of this, we can work out the total velocity of this rowboat. Someone here is trying to actually get across the other side of the river or stream, and they've got a rowing speed of 4 metres a second using their oars. They've got a current going off to the right here of 3 metres a second. So here we're trying to find out what the total velocity of this boat will be, because we'll not go straight across the river to the person. It's more than likely to go up an angle. So can we work this out as a total? So if you use your vectors there, we want to do this as 3 off to the side there. We do that way around with the river first. Then the boat speed of 4, and you're going to get a total across up there. There's your total there for velocity with an angle, and it's 90 degrees. So again, you would do VT equals the square root of 3 squared plus 4 squared. I've chosen very easy numbers here. You get 5 again, and again you're going to do tan theta. In this case is opposite over adjacent, which is again 4 over 3, which is going to turn out to give you a theta as tan to the minus 1 of 1.33, and you end up with 53.1 degrees again, because I've cheated there. Alright? You could quote this then in degrees true as well, by the way, which I'll come back to in a minute. What I want to know is if I'd actually added these other way around, would it have made much difference? So if I'd added this as a 4 first and the rowboat first, and then added the river current across, would I still get the same vector in the middle through here going like that? The answer is yes. Okay. Obviously the angle you get here will be quoted from the north down, around there, but it still would be the same direction when you look at it overall. So if you did do that here, you would find you get an angle of 53 from 90, like that, and so you're going to end up with 26.9 degrees. Okay, and that was still okay as well. So if I saw a triangle like this with 26.9 degrees for my theta there, and I still got the answer 5, then I would be fine with that as another way of doing it. So it doesn't really matter which way around you add them. So if you add them A plus B or B plus A, you get the same answer. This particular one, this question 2A here, the ocean current one, a lot of people, as soon as they see this, make the mistake of going, I am going to add this vector and this vector like that, because that's the way they are in the diagram, and therefore my vector total is this way somewhere. And they then have to guess whether they think it's going downwards or whether it's going upwards. Because the reality is not doing either. If you look at that boat here, it's got a velocity off to the side here, say easterly, and it's got a northerly current, okay? So it should be pushed this way. So this is the result when you're trying to use a mathematical model to find the vectors, would not work. You need to actually add them tip to tail always. So if we look at doing that here, and adding this tip to tail, go back to the start here, we can put the velocity of 8 in first, like that. Then do the velocity of 6, and then it makes sense that the total vector should be up here. Sorry, that's not a very straight line. And that's what we're going to add together. So you're going to do the square root of 6 squared plus 8 squared, which turns out to be the square root of 100, which is actually 10. All right. And again, your theta would be 10 to the minus 1 of opposite side over hypotenuse side. You get an angle there. And that should be 36.9 degrees. Now that's not degrees true. If you're doing this as degrees true, and you started from true north here, I mean like that to your real vector here, if that's 36 in here, to get your true north you're going to have to do 90, take 36.9 to get your result, which would be 53.1 degrees. So it's 53.1 degrees true, that is. The other way you can describe this is to say it is east going 36.9 degrees towards north. So you will see some books go like that. It's 36.9 degrees north. So it'll tell you which way to start and which way to end up going towards the north. So watch out for those as well. The key thing here is to never add them as tail to tail. All right, thanks for that.